This is our second example of an application of modular arithmetic, and it's called cryptology. So cryptology can be broken into two parts, cryptography, and that's where you're writing secret codes, for example, encrypting data. And the second part is cryptanalysis, and that's when you're analyzing and breaking secret codes. So some examples where this is useful is online banking, encryption, and cryptocurrency, where you have digital money without the need for banks. In this example, we have some secret code here. So F, and then ILSB and VLR. We don't know what this means. So this is an example of ciphertext. So it is an example of secret code that has to be decrypted if we want to understand what this means. So this ciphertext was encrypted using what's called a cyclical coding scheme by substituting each letter of the alphabet with a letter that's an unknown number of letters after it. In other words, we've just sort of shifted the alphabet. So the question is, how can we figure out the message if we know it's a cyclical coding scheme? So what I'm going to do is I write the ciphertext down, and what I'm going to do is I'm just going to move one letter. I'm going to use the next letter in the alphabet, okay, for each of these letters. So, for example, F, the next letter is G. So if we had moved one letter in the alphabet later, we would have G. The letter that comes after I is J. The letter after L is M. The letter after S is T. The letter after B is C. The letter after V is W. And then we have M. And then we have S. So this doesn't really look like anything. So the cyclical coding scheme is definitely not just advancing our alphabet one letter. So I'm going to continue the process, and I'm going to move another letter forward. So what comes after G? H. And then J, the next letter is K. The next letter after M is N. After T, we have U. After C, we have D. X, N, and T. Again, this doesn't really look like anything that makes any sense to me. So this is if we advance one letter. This is if we advance two letters. So I'm going to go another letter. So after H, we have I. After K, the next letter is L. After N, we have O. After U, we have V. After D, the next letter is E. After X, we have the letter Y. L, M, N, O, and then T, U is the next letter. And so now we can see, oh, so the secret message makes sense to me now. It's I love you. And this is what we call the plain text, right? So once we've decrypted, the ciphertext changes to plain text, and this message now makes sense to us. So basically what happened was that in the cyclical coding scheme, we substituted each letter of the alphabet with the letter that in this case was 23 letters after it. So we will be using M to denote the shift, but for example, the letter I, if I look at the letter that's 23 letters after it, that would be F. And just to make it absolutely clear, what I'm saying is that the letter I, in the I love you, was encrypted as an F, okay? But if we look at our alphabet here, we have, in order to get F, if I look at the letters after I, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So that's 23 letters after I. And if we want to just summarize the encryption, we could say, okay, F, G, H, I, J, C, D, E. And so here you see the big picture in all of the translations. So to encode the message "I love you," or to encrypt the message "I love you," we just have we would use these love, and then you, V, L, and R. So you're probably wondering, how is this related to modular arithmetic? So in order to understand the relationship to modular arithmetic, we're going to assign a number to each of the letters. So 1, 2, 3, D is 4, 5, 6. So we've assigned a number to each of the letters, and notice that Z is the 26th letter, which is congruent to 0 in mod 26. So in the message "I love you," the letter I, okay, note that that is the ninth, number 9, it's the ninth letter. So that corresponds to, and I'm going to use the notation P for plain text. So P in this case is 9 for the letter I. And this encryption, what we did was we added 23. Okay, so we had an encryption that used 9, we shifted by 23 places, so we have 9 plus 23. Okay, but that gives us 32, and there's only 26 letters, so we take mod 26, and we have that 32 mod 26 is equal to 6. And so 6 is the value, is the ciphertext. So this implies that the ciphertext, and I'm going to use C, the number of the ciphertext is C, and that corresponds to the letter F. And we call this number here, recall, the shift, I'm going to call M equal 23. In general, if C represents the position of the ciphertext, so that's the number, and P represents the number or the position of the plain text, okay, and then M represents the shift, okay, the translation. Then the ciphertext number is given by P plus M mod 26. So this captures cyclical alphabetic encryption. And if we want to decrypt, we can use P equals C plus N mod 26, where P is the number for the plain text, C is the ciphertext position or number, and N is given by 26 minus M, okay, where remember M was our shift. For example, in the last example, if we wanted to decrypt, for the letter F, which was the first letter in the encrypted "I love you," F had a position or a number 6, okay, and so we would use the number for the plain text would be given by C plus N, where N is 26 minus 23, which is 3. So we'd have C plus 3 mod 26. So that would be 6 plus 3 mod 26, which is just 9. And as we know, ninth letter in that case is just I. So that P is equal to 9, and it's the letter I. Okay, and so here we have that the ninth position or the ninth letter is just I. So that's our plain text. So that's for the "I love you." So let's do an example. We're going to use the cyclical alphabet encrypting code that shifts each letter 12 positions to encrypt food and then to decrypt PAS or PAS. So let's start with food. Now notice that M is equal to 12. That's our shift. And the way that we can write the congruence is P plus 12 mod 26. So I'm going to just write the 4 letters here for food. And if I go back to our chart, you can see that F corresponds to P equals 6. O corresponds to P equal 15. And D corresponds to P equal 4. So using those values of 6, 15, 15, and 4, I'm going to write out this formula for each of these. So this means the ciphertext would be given by 6 plus 12 mod 26. And the ciphertext here would be given by 15 plus 12 mod 26. This would be the same because it's the same letter. And then the ciphertext would be given by 4 plus 12. So it would be this position, mod 26. So let's work out the math here. So 18 mod 26 is just 18. And here we have 27 mod 26. If I divide by 26, the remainder is 1. And here I have 16. This will also be 1. And then I have 16 mod 26, which is just 16, since it's less than 26. So now I'm going to be looking for the 18th position, the first position, the first position, and the 16th position. Okay, so in the 18th position, we have R. And in the first position, we have A. And again, we have A. And in the 16th position, there's a P. Okay, so the 18th letter is R. And the first letter is A, another A, and the 16th position or letter is P. So this would be our encryption of the word food, just R-A-A-P. Okay, so let's work on part B and to decrypt PAS. So again, I'm going to remember that in this case, we need to figure out what N is. So N is 26 minus M, which is 26 minus 12, or 14. And to decrypt, we need the plain text position is going to be given by the ciphertext number plus 14. So that's where the N comes in, mod 26. So I'm just going to write P, A, and S over here. So the plain text position or number will be given by, remember, this formula. So let's take a look and see what the ciphertext value is C for P, A, and S. Okay, so we are going to look for the positions or the numbers corresponding to P. So here we have a 16. And for A, we have 1. And for S, we have 19. So these are the values of C that we need. So we said in this case, C is 16. And we're going to be adding 14. Mod 26, and in this case the plain text will be given by C, which we said was 1 for A, and plus 14 mod 26, and then we have P equal 19 plus 14 mod 26. So what is the remainder when I divide 30 by 26? It's 4. The remainder when I divide 15 by 26 is just 15, and here we have 33, and the remainder is 7. Okay, so let's go back, and what letter is in the 4th position, in the 15th position, and the 7th position? So the letter in the 4th position is D, the letter in the 15th position is O, and the letter in the 7th position is G. So we have D, O, G. So going back, this corresponded to D, the 15 is for G, O, and then 7 is for G. So If we decrypt PAS, we just get dog. So this type of encryption is obviously really easy to figure out because it's just a shift of the alphabet. A more difficult type of encryption to decrypt uses a slightly modified congruence. And in this case, we we multiply P by some number A, and the only restriction, A and 26 cannot have common factors. Okay, so this is the only change right here. Let's do one last example using this slightly more difficult encryption. So we're going to use the congruence 5 times P plus 11 mod 26 to encrypt cats. So I'm just going to start with my letters here, C, A, T, and S. And so how do I find the ciphertext position? So I'm going to start with the 5 times P. So the position of C we know is 3. A, B, C, plus 11, mod 26. Let's go ahead and do A. So this would be, again, we have 5, and we know P is 1 because A is the first letter. And then we have C. T is the 20th letter, so we have 5 times 20 plus 11, mod 26. And S is right before it, so we have 5 times 19 plus 11 mod 26. Okay, and then this is equal to 26 mod 26, which is just 0. So that just corresponds to Z, right? And then we have here 16 mod 26, and that's just 16. And here we have 111 mod 26. So if I divide 111 by 26, the remainder is 7. And here we have 106 mod 26. And if we divide 106 by 26, the remainder is 2. So the 0th, or you could say 26th letter is Z. The 16th letter, if we go back to the list, is P. The 7th letter is in the alphabet is given by G. And the second letter is given by B. So using this encryption, cats would be encrypted as Z, P, G, B.